now I want to show to you guys on design rainfall using the Gumbel distributions. So the first step, as I mentioned before, okay, you need to determine the annual maximum rainfall. So as you can see in this slide, I already give you the annual maximum rainfall. Okay, this one, annual maximum rainfall. So if you have a data series, for example, 1 January 1960, okay, if you have a daily data which is starting 0100, so probably you have 0, and then the second hours you have 2. So until 31 January, 31 December 1960 at 24:00. So you have, for example, 2 millimeter. So you find the maximum data for the 1960. So this one, if you find the maximum data, so this one we call as the annual maximum rainfall. So you put in this table. So this is an example how we determine the annual maximum rainfall. So in this example, okay, the hourly rainfall have been covered at the GPS Lucky stations, covering a period of 22 years. So from the 1992 until 2013. So it's almost 22 years. And then estimate the intensity of the hourly rainfall with 100 years of written periods. Okay, based on the Gumbel distributions, we have this formula, which is xt equal to the mean plus coefficient times with the standard deviations. So the first thing, you need to find the mean of annual maximum rainfall. So for this case, okay, if I take the average one, okay, you total up this one, you guys will get 125 millimeter per hours. And then by using the same concept, you find the standard deviations for the wall data. So if you substitute with the formula of the standard deviation, and for this case I using the Excel, okay, you just type the standard deviation and you select all the column, okay, they will give you the value, which is 49.628 millimeter per hours. Okay, and then you have K. So the coefficient, or we call as the frequency factors. Okay, you have a formula, and also you can obtain the value of the coefficient factors by using this table as being displayed here. So you have a KT, and then so for the KT, so since we want to find the T, the return period for 100 years, so ARI is 100 years ARI, and then KT you just substitute into the equations. So if you solve this one by substitute all the mean and the standard deviations, okay, you guys will get 284.62 millimeter per hour. So that's how we solve it. And then if you want to develop the rainfall intensity, okay, something like this, okay, you need to find the return period for others. For example, you have 2, 5, 10, 20, 50, and 100. So if using the log graph, okay, log graph of the 10, okay, you able to plot the straight line, something like this. So that's how we determine the rainfall intensity based on the return period by using the Gumbel equation. Okay, what happens if you want to develop the IDF curve by your own? Okay, so if you want to find the IDF curve, okay, you need to find the first step. You need to find the return period for each duration. So for the example that just I give to you guys, this one is the maximum annual rainfall for interval 1 hour, which is the durations is 1 hour. So if we want to find for the others durations, for example, 2 hours, 1 day, okay, you need to aggregate the data. That's mean for 2 hours, okay, you need to find the cumulative of the 2 hours of the rainfall. So you will get the value. And for the 1 hours, for 1 days, you need to find the cumulative of the rainfall for 1 days or 24 hours. So our previous example, okay, this one just for 1 hours. So if we have this type of the table, you have 15 minutes, 30 minutes, 1 hours. Okay, so you can put your data on this cell. Okay, that's how we obtain the return period for 1, 2 hours, 3 hours. Okay, probably I have this question from you guys. Doctor, how we obtain for 15 minutes and 30 minutes? Okay, so for our case, since the observed data that we obtain by the DID is 1 hours, okay, we cannot find for 15 and 30 minutes. We cannot find unless you deploy another method we call as a disaggregate methods. So for your level, okay, I think I do not introduce that method to you guys, okay, because if we want to touch a method for this aggregate method is quite it's take time lah. And then there is a lot of the research have been conducted on how we disaggregate data, okay, for example from 1 hours to 30 minutes and 50 minutes. So a lot of methods that we can deploy, but for the level for you guys, probably that one is not covered in your in our scope of these sessions. So we just focus for 1 hours, 2 hours, and 1 day, and etc. So this one, after you produce this table, okay, 15 minutes, 30 minutes. So this one for you can produce this type of the tables. Okay, it's the same thing. Okay, we have 1 hours, which equal to 60 minutes, and then we find the ARI, the return period, okay, for 2 years, 5 years, 10 years, until the 100 years. And then if you guys rajin lagi, okay, you can find 12 months, 6 months. So you can get this sort of the table. And then as you can see on the right side of the column, you have 3 hours, 6 hours, 12 hours, 24 hours, until 72 hours, which is this one 3 days. This one 48 is 2 hours, 2 days, and then this one is 1 day. Okay, you need to aggregate the hourly data first, okay, which is 1 hours you need to convert to 3 hours, and then you need to convert to 6 hours, 12 hours, and 20 hours. So this one quite, for me, the procedure actually is not very straightforward. Okay, the procedure actually is very straightforward, but it is very tedious procedures. Okay, memang agak renyah sikit lah if you want to derive the IDF by your own. Okay, after you complete this table, so this is the truth of the moment. So you akan dapat lah the IDF curve that you calculate by your own. Okay, so starting the return period 6 months until the 100 years. So this one is your TR, your return period. And then the y-axis, okay, is a rainfall intensity in millimeter per hours. And then you have the storm durations, okay, which is 1 hour, 3 hours data that you obtain, which is for the x-axis. So you have this almost straight line, okay, if you plot in the log graph. Okay, baik. I think that's how we derive the IDF curve. So make sure you guys really know on how to derive and estimate the rainfall intensity. Okay, we go to the probable maximum precipitation, PMP. So PMP actually is defined as the greatest dip of the precipitation for a given duration that is physically possible over a given point or a specific area at certain time of the year. So the estimates of the PMP are required for calculating the PMF, which is probable maximum flood. PMF, which is the design flood for the spillway of the dam where no risk of the dam break can be accepted. So this is how we want to use the PMP. If you construct the reservoir, for example, we want the reservoir do not break down. Okay, that's mean you need your reservoir have been capable to face any rainfall intensity, rainfall volume from the heavy rain by have proper design on their spillway. Okay, ingat lagi tak spillway yang tadi yang lecture saya yang saya mention tadi. Okay, so we have the inlet, we have the primary outlet, and then we have a secondary outlet, or we call as a spillway. So the function of the spillway actually, lebihan air, okay, akan mengalir ke spillway. Dia macam satu parts yang maksudnya dia tidak dikontrol, okay, tidak dikontrol. Maksudnya lebihan air daripada empangan, okay, jika melebihi satu tahap, okay, maksudnya tahap yang berbahaya, okay, air itu akan mengalir ke spillway. Tujuan spillway itu dibuat supaya kita tak nak our reservoir, okay, boleh breakdown. So you imagine kalau tak ada spillway, okay, air tu akan increase until one certain of the level dan dia akan melimpah keluar daripada reservoir. So bila dia melimpah keluar daripada reservoir, okay, dia boleh menyebabkan our reservoir punya wall, for example, okay, kalau you have a concrete, if you have some sort like bund, okay, ataupun earth wall, okay, dia boleh menyebabkan you punya wall tu eroded dan boleh menyebabkan you punya dam tu of the wall will be broken, will be break. So normally on this situation we don't want that thing is happen. That's why we design the spillway. So bila air naik, okay, air tu akan terus pergi ke spillway untuk mengalir keluar. Itu tujuan why we propose the spillway and how we integrate this concept with the PMP. So for the small area, okay, basically PMP we can estimate by using the Hutchfield, okay, which published in 1965. So Hutchfield, okay, you guys can using this formula. So you look this formula, ada sama tak dengan formula yang untuk estimate the design rainfall? Okay, kalau kita tengok sebelum ni, this one. Okay, So basically the formula is the same, which is the X PMP. Okay, you guys will using the annual maximum of sorry, you guys need to obtain the mean of the annual maximum first, and then and also this one standard deviations, and then times with the km, which is the factor. So you can see the factor you can using this formula. So this is the simple way to estimate the PMP. So this is the example of the study of the PMP by using the half field. And then if we're using the km is equal to 15, so this is and then lastly we're using the Gumbel here for the 100,000 years ARI. So if we look on the duration 1 hours at the Padang Besar, so you can see the half fields is around 194. But if you're using the km is equal to 15, okay, so the value is much greater. But if you have a Gumbel for 10,000 years, okay, you can see it's low as compared to the half field. And then if we compare with the MASMA, okay, if we're using a MASMA or the HP01 2015 for 100 years ARI, so you guys will get 248.64. So this value actually is quite near to the km equal to 15 minutes. So which one is more valid? For our case ni tidak ada istilah lah yang mana satu yang lagi tepat. Okay, so it's up to you guys whether you want to consider if you want to develop the PMP, you guys can using the half field, okay, as your main calculation. Either one, if you want to compare with others method, okay, for example Gumbel, ataupun if you want to using the MASMA, okay, yes you can. Okay, at least we have some benchmark which one that we want to use. Okay, for example you have these cases, okay, for the half field, and then you have km is equal to 15. Okay, kenapa kita letak km to equal to 15? Okay, because there is some literature that said km need to use 15, and this value able to represent the PMP. There is some statement from the literature review. Saya tak ingat mana saya dapat, but there is. Okay, saya kena check balik lah with the literature review. So you have 1, 2, 3, 4. You have 4 results. If you submit to the authorities to determine the PMP values, okay, mungkin you boleh ambil this value, which is km equal to 15, because the km equal to 15 gives you the highest value of the PMP. So it will make you very confident that your punya reservoir able to sustain the height or heavy rainfall, okay, up to 301.7 millimeter per hours. So that's how we play around. Sebab kalau kadang when you submit the data, okay, to the authorities, contoh JPS, kadang JPS dia nak several options. Maksudnya you have the first option, second option. For our case, we provide 4 methods to determine the PMP. Okay, and then during the meeting, okay, we can discuss, and the JPS have an option to select which one is better. Okay, because if you design, for example, 301.7 millimeter per hours, so your facilities, your spillway will become, probably need to very large spillway, which is increase the cost. Okay, and then probably your punya wall of the volume of your reservoir pun need to be increased. So if we increase the cost, but if we select the lowest PMP value, for example, this case is around 161.91, okay, millimeter per hours. Okay, it will reduce the cost because the spillway that we need to design is not no need to very large. Okay, because it taken a very low value of the rainfall, which is the PMP value. So it depends on the authorities to decide. But we as a consultant or the engineer, okay, we need to supervise lah to the JPS which one is the better. And for this case, if you want to construct a reservoir, normally we take the most highest because we want to secure our reservoir. Okay. So this is the PMP for several stations, and we do some special analysis and we display in terms of the map. Okay, this one is my current student have conduct their final year project, and this is their funding for the 1 hour durations. And as you can see from his result, okay, if you go through on this graph, okay, this one is location of the reservoir, Timataso reservoir, which is one of the reservoir in Perlis. Okay, and then the PMP is quite high value. Okay, at the below of the reservoir. Okay, if you want to reconstruct the reservoir or if you want to upgrade our reservoir, you guys can using these results to helping you.